maybe premature. Anyway, thank you. But I would particularly like to thank the host committee for their kindness and the efforts they are making to get me somewhere to spend the night on Friday night before I fly out Saturday morning. I know you've had a full lunch, so I suggest you sit back, relax, and I will take you on a magical ride through water. I began my work on water about 15 years ago when a colleague asked me if hot water really froze before cold water. I told him yes, and he said why. I did a lot of this and couldn't answer the question, so I determined to answer the question. I successfully answered that question in my humble opinion, but on my way to answer that question, I observed many interesting phenomena. The previous statement up there, I think you all will agree that if there's magic around, it is in water. And I will start by showing you some of that magic. The first few slides, I will go pretty rapidly. Then I will slow down and give a little bit of detail. One of the interesting things I observed is you can wind up with upside down convection. You can sit water here where the bottom of the container of water is just above zero, drop it just below zero, 700 milliwatts immediately, quotation mark immediately, sinks to the bottom, the whole column of water is cooled to zero or below. Nope, one too far. You can turn this on and off simply by bringing the base of the container above and below zero. Below zero, above zero, temperature up. If the water freezes, the gig is up. The whole game is over. On my way to, I like to move around a little bit. On my way to solving that mystery of 2,000-year-old mystery of hot water freezing before cold, I decided when I had the answer that I would convince myself I would prove it by sealing a sample of that water in a valve and holding it as long as I could. As long as I could, until I lost power in the building. So after 400 something days, the power was off and the water was still at minus 15 degrees. I already knew ahead of time that this water would not freeze until I dropped down to around minus 17. Cut the equipment back on. A year later, put the same valve in, dropped it down to minus 13, and boom, it did not freeze till I got back down to where I normally expected it to freeze. And there's been many questions about supercooling and how the water had to be perfectly clean and all of this stuff. Baloney. Any water that I've ever tested can be supercooled. If you define supercooling as a minimum of 1 degree below 0 Celsius. And just about any other liquid I come across, you can easily supercool it. There are certain caveats, of course. I stand up here and say easy. You try it and it'll never work for you. One of those magical things that revert back to this bottle. So I can take this container of water, put it in the cooler, it'll freeze at a unique temperature. Let's say a minus 3 degrees. Break it out into individual containers, seal them. They will each freeze. When I say freeze, I mean latent heat being released and the initiation of freezing. Freezing actually occurs at 0. They will each freeze at a different temperature. Irregardless of the initial starting temperature, we got to do the hot water business where you start at above 100 degrees, and in all cases they freeze at the same temperature. As long as the container remains sealed. Now you can supercool water or you can stop water, prevent water from supercooling, and that is fairly easy to do. We've got 2 containers here in the cooling pad. They both supercool. You instantly, when they start not supercool, they freeze when the temperature reaches 0. Only if you have a perfect nucleation agent in it. And the perfect nucleation, there's only one perfect nucleation agent, and that's ice. So I have liquid nitrogen, ice crystals falling down, and as soon as the water gets to 0, freezing, the onset of freezing. Screen one of them, no ice crystals in, one open, freeze at 0, the other one goes to supercool and stay there indefinitely until you do something. Remove the screen and it freezes. right containers to put it in. So a lot of containers are good containers, these bottles. Put the bottle on the shelf, forgot about it. Come back 3 years later, this is what it looked like. I am losing water all over the place. And one of the ways I work is from observation like this, start experiments. So I recently, a few months ago, I went out and bought a series of water bottles, weighed them, put them on the shelf. Every Monday morning I go in and weigh them. They're losing between 20 and 40 milligrams of water per day. And I expect them to collapse like the one you saw here before. Now, so what happens when you take water and you freeze it? Well, the first thing, as I said before, if you don't have a perfect nucleator in it, it will supercool. It'll cool to zero and continue until something happens, latent heat is released. If you have a couple of electrodes in there, they will indicate when you break those bonds to start the freezing process. And depending on the configuration, you get a nice sharp signal at the beginning, and sometimes when this is pure water, when you now have solid ice. With the thermocouple in a container of water, you don't know when the last few molecules, you don't know where they solidify. So the thermocouple will never give you an accurate temperature when you have solid ice. This is just the same example, a little cleaner showing that we have beautiful activity there. We'll use this a little later. So you can do this in dirty water. You can do this in dirty water. You see the same thing here. But other things happen while the water's freezing. You all know that we can take salty water, dirty water, and the ice in it is considerably fresher or purer or clean up, whatever term you want to use, than the original dirty, muddy water. This is the electrical activity that's occurring during the freezing process. I'll show a slide later where I have the probes and so forth. And again, I won't spend much time on this. This is taking you through the easy ride, the fanciful ride through water. Now, you can take this water and confine it in, say, like a drinking straw. Put 2 electrodes in it. Supercool it to freeze it. You don't know ahead of time, but one end will give a positive signal and the other end will give a negative signal. For this sealed container then, as far as my experience is concerned, which has lasted for months, that is now the polarization of the permanent direction of the electric charge in the water. This end will always be positive, and this end, other end will always be negative. So I cycle through this, you can see thousands of seconds, automatic. Mechanically switch ends, and the other is negative because I'm looking at this end now, or vice versa. Switch back, and the other one positive. This requires that you put it in a confined arrangement. If you put it in a large container, you don't get the beautiful one pulse on both sides. Here you get multiple pulses. Plus, minus, plus, at the release of latent heat. I will talk about what's going on there in a little while. This is still part of that fanciful ride. Now, to a little magic in detail. Quite familiar. All of you are probably familiar with this. It's been around in the state for hundreds of years. I rewrote part of my session after Jerry's book came out, and I decided to take advantage of it. So he got the system here where he's showing with the infrared camera that there's something going on in the water. But this is hot water. This is warm water. So I take this system and I cool the bottom of it. This is a typical test tube that I use. And remember that I talked about that upside down convection? And in his case, I'm pretty sure he's talking about warm water moving up, cold water moving down. I'm talking about cold water moving up, warm water moving down when I go through this scenario here, just cooling the bottom here, and the top here can be at about 20 degrees. This is a simple system you can work with, and I like to do stuff that people back in high school and even grade school. I've had the 8th, 6th graders writing me, asking me for help on that science project, particularly on the hot water freezing before cold. And so I try to do everything where it can be reproduced with almost no expense. Pellet cooler down here, styrofoam insulated, because I want to cool from the bottom and I want no heat coming in from the side, but heat coming from the top. Now, related to something we were just talking about here, another magical thing happens when you this container like I saw before, and I had it set up where I can tilt it. So I've got a tube in here, I turn the cooler on, I start cooling the bottom, the temperature drops down. And you notice here that this thermocouple, either on the outside or the inside of the glass tube, it doesn't matter, is 2.7 degrees higher than the other one. Now, if this is tilted south 15 degrees, then I don't know what I wrote there, but if you tilt it 15 degrees north, redo the experiment, the reverse in temperature. East and west. So what you have here, basically, is columns of cold water moving up this container, and the warmer side on the other side moving down. So this is a dynamic, stable system. It is stable enough so that we take it hours later. So we've got this tube sitting here. We can do that 15-degree rotation and just looking at two of these thermocouples, and you can see the switch. This is very, very stable. This is when you can see down here when I did the careful rotation. Boom, boom, and it just go on, and this will go on for days and days and days. It is remarkably stable. It's as if you had stable pencil-like columns that you can't break apart. However, I will break them apart in a minute and show you what happened. Now, this is very interesting and exciting to me, this observation. So I've got this test tube with a series of thermocouples outside and inside. You don't have to worry about the thermocouple interfering. 1 centimeter apart, this 1 centimeter in diameter, 1 centimeter apart here, and here's the indication of the blue one here, and the red one on the opposite side is 4 degree Celsius difference. Go vertical in this column right here, less than ½ degree, and you cover 2 centimeters. So the vertical thermal gradient is next to 0, the horizontal thermal gradient is 4 degrees, and this again is stable. If I switch this 15 degrees, the red would drop down, the blue would go up, and these two would stay essentially unchanged. Magic. You can get really good magic now when you mix, quote, 2 kinds of water. And when I talk about kinds of water, I'm talking about regular water with its small percentage of D2O, and then regular water with added D2O in increasing concentration, homogeneously mixed. So I take and put a couple of drops of D2O in here, very careful from the top. Let it sink down. Thermal oscillations will begin. We don't have time to go into detail, but thermal oscillation will begin at some period down here. And these oscillations, with respect to these thermocouples, that's what they look like on these two. But the temperature is varying around this tube and this tube. And notice they're out of phase. Now there are 2 more on the other side. The same thing is going on, but I left it out here to show it on simplicity. So if you looked at the other side, which I don't think I showed here, you would see the same thing, but they would be out of phase. So the 180 degrees is out of phase, 180 degrees out of phase, and this can go on for hours. So to confirm that experiment, I decided to add a fixed volume of water with different concentrations of D2O in it. All the way from pure water, add pure water here, and nothing happens. This is the, you're looking at the thermal gradient in the system. Added with 12% D2O added and homogeneously mixed, 75 milligrams. There's some perturbation here, some disturbance, but it's pretty soon settles out. Add a little bit more and a little bit more. If you get up to 50%, you're at the range now where this spontaneous oscillation will begin, and will continue for some period of time until it actually homogeneously mix all of the D2O with the H2O, and now you have only 1 kind of water, H2O with D2O homogeneously mixed in it. That's what that thermal oscillation looks like. I'll smooth this curve a little bit, get rid of the noise, but this is just absolutely beautiful. I hope I get a yes from somebody. This is spectacular, and this will go on and on and on. This is what if you look at the frequency, in 70 minutes, from that example I showed showed before, this is what it's decayed down to. When it started out, it was roughly 1 revolution per minute, and it took about 2 minutes to do a revolution down here. So what we have in there, which I'll get to later, are a rotating sail. We'll get to that later. Now, I apologize for having to go so fast, but I have so much beautiful information. I want to put it out there. If anybody wants anything, my PowerPoints are available for here, or you'll be able to download them from my site pretty soon, because this is just too beautiful to ignore. Now, the reason this all occurs is because the unique property of water of having a maximum density at 4 degrees. So once you get water at 4 degrees, if you want it or cool it to become less dense and it works against gravity, it tends to rise. That's the key to the whole system. So I have a system here. What happened?
Press the button. Press.
No. Can somebody bring me back to life? Anyway, so I can talk about it. Anyway, so I have a system here, bottled water, uniform temperature, no thermal gradient. I can do this show just as well. It's better than slide. No thermal gradient. 20 degrees, 20 degrees. Put this in a cooling bath, insulated here, minus 10 degrees, it's 20 degrees up here. 4 degrees is somewhere in here. That's the maximum density. So the water below this 4 degree want to rise. The water above it, we're coming back online, almost. The water above it want to rise. So I was able to show that this was happening in the case that once you start the cooling process, this 4 degree phase moves right up. And that's here. I got thermocouples here. This is what happens when this 4 degree maximum density phase moves past each of those thermocouples. You can see the temperature drop, drop, drop. So I'm walking by, it's dropping, dropping, dropping. And if I look at it horizontally, you can see the same thing here, where the thermocouples are this way, and you move past it, that's max 4 degrees. So there's a beautiful system here that starts at the bottom and moves up to the column. But if you interrupt that, you can now get a thermal gradient. So this is the system uninterrupted. It's moved all the way up to the top. So I add some D2O. My animation is not quite showing here, but we won't worry about that. So I add a small amount of D2O, like right in here, and the buoyancy force from the density breaks that up, and it becomes uniform D2O mixed with H2O. So I have just enough energy from the buoyancy to break it up, depending on how much water I add. If I add heavy amounts, like 50% here, it can only break up part of it. But you still have this boundary up here. You got the density gradient here, the boundary here, D2 up here. The water now, the cold water cannot rise past that boundary. So it bumps into that boundary. And let's get it started here. It bumps into that boundary and sets up this circular oscillation. So a thermocouple here sees a temperature fluctuation. One above this line does not, and I didn't show one down here, one at the bottom. It does not. They are totally flat. So you got this constrained region here by having the thermal and density gradient in that, where you can set up a system, and this will continue for hours. And this is just spectacularly beautiful. I'll skip that because that was my first pause if I ran out of time. I mentioned before that you can look at this system and you look at all 4 of them. That's what you see. This is the oscillation with all 4 of them. On this side, and you can see this is going for 5 hours. I looked at it right here. Frequency here. Look at it here. It slowed down some, but it's still going. Quotation mark, big quotation mark. Temporary perpetual rotation. As long as I can maintain that thermal gradient and that density gradient and set this system up by adding a solid, and I prefer to add heavy water, but you can add other materials. But you have to add something to stop that convection. Now, again, someone, the talk that's following me is going to talk about something happening when water sits for a while. So now you can add D2O to water. And when you don't add D2O to water and you set it in the system, in the first few hours, it's all cooled down, as you saw on the earlier slide, to near zero. You add the D2O, so you have two kinds of water, which will inhibit convection. The cold water can't move up, so the hot water doesn't cool. So the system just sits there with a thermal gradient. It cools down a little, but it sits there with this permanent thermal gradient. Spontaneously, out of nowhere, I have no idea why, somewhere down at the bottom, it'll start oscillating. It will now break up those clusters of D2O water, mix them homogeneous with regular water, convection begins, invert, upside down convection, the system mixes, and boom, you cool down to where the whole column is now cold. Going on right now, I set a system up before I left, and I'm at day number 10 in this range. And at some time, hopefully before the computer crashes or something, I'll be able to observe this phenomenon occurring 10, 14 days later. Why the spontaneous mixing? It's a good question, but one that I love to operate on. Again, you can see the frequency down here in time. Again from Jerry, thanks, you gave me something to work with. So clusters. So the way I make my clusters, the measurement clusters, I put a little dye and some heavy water and put it in. And if you do it carefully, so this is heavy water clusters, regular water clusters, and so forth. So that's the key, is to have this homogeneous, inhomogeneous mixture without breaking them up. And size has something to do with, remember I showed that too, where the polarization will be uniform, but if it's large enough so that all the clusters can rotate, then you will not get a uniform positive or negative pulse. So I suppose it is really dipoles forming inside the clusters. But to test this all out, I put a simple system together with water in it and asked how long would it take for a heat pulse to go from here to the outside. So you dump this into an ice bath with unmixed D2O in it, and regular water mixed, it takes this long. And D2O unmixed, it takes a minute longer for that photon to reach there. For that water in the center to realize that the outside is cold. It is having trouble getting out there. And another way to look at that graph, if you put a whole series of the thermal comes really close together, and then you can see the thermal fluctuation here. The photons are being scattered around, so one thermocouple is getting hot, and the other one's getting cold, and you can see a temperature difference here of almost 3 degrees. And these thermocouples are within a cubic centimeter of each other. And you mix this up, simply by shaking it up, and it looks just like the regular water, nothing. Nice, smooth, continuing process, cool down process. Another way to see that you have clusters, and this is low-tech, determine that you have clusters, and look at the cooling curve. Regular water, this is what the cooling curve looks like, with a thermocouple at the bottom and a thermocouple at the top. Add your D2O, and it's drastically changed. Take this one, shake it up, break it up. You have the same kind of water. I don't care what kind it is. It's the same kind, uniform, homogeneous, and you're back to what it looked like before. And just a few more slides, and I should finish early. You can set these rotating cells, I like to call them up. I can't do it on purpose, but they do occur where you have one cell, or you may have 3 at different locations. This is the case where I have 3 at different locations, and you can obviously see the difference here. And they're all sitting there rotating for many, many hours. Why they spontaneously quit here, I don't know yet, but you can physically make them stop by simply shaking the system up. This is the case where one cell developed low, and it rolls up through the column. And as it gets to each thermocouple, you can see the oscillation patterns. As it approaches, as it leaves, so it rolls right up to the thermocouple. We've calculated the velocity and so forth. And these are slides I showed at a conference a couple of years ago. And this is back to since I have a little more time, this is back to the rotation dishes. So when you look at all 4 of them here, you can see the blue, the 5, but I left the others on the graph so you can see what happened. So So you can see there's a little bit of change in degree, but you can see right through this one, almost nothing happened. So you have these columns, and for the life of me, I haven't quite figured out how I get all the way across with so minimum disturbance, but without breaking them up. How I can switch from 3 degrees up here to 1 degree down here. But for this to occur, the temperature must be below 4 degrees, and it can't be a little bit above zero, or a little bit below zero, but you must have that thermal gradient. And this is looking at the whole system, which may give some additional details. In detail, when you switch and what happened to each of those thermocouples. So you can see the blue and the blue and red make dramatic switches, but I have to go around all the rest of them and go one to the other. And there's a little bit of bump on the center one here. So am I going through that, or am I going around it? Or how do I get from here to here without major disturbance here? There is considerable disturbance on the green one here. So there's still lots of questions, but it's still magical for me, and I'm having a lot of fun doing it. So I mentioned before, don't let me go over. How much time do I have?
5 minutes.
Oh, I'm going a little too fast. So I'll leave time for questions. So this is again showing the same type of thing with the system vertical and looking at all 3 of them. This is the center one, and these are the 4 that are in the same plane. I think I will stop here to allow the opportunity, in case there's one question for you to ask me.
So you showed many beautiful and provocative experimental results. Your interpretation is that these are basically thermal gradients, because thermal gradients are well known throughout nature. However, if you really consider the difference in density as a function of the difference in temperature, it's really small. A 0.1% or something like that over a few degrees. However, there's another possibility, and that is a possibility, we've shown many examples of charges all over the place that arise as a result of exclusion zone buildup. And if you think about the forces generated by these charges, they're huge. The difference between the gravitational pull of mass and the force produced by 2 charges, they're both inverse square laws, but the constants differ by 10 to the 38th. So it means that these charge forces would seem to be so much greater than density differences. I wonder if you would consider the possibility that some of these movements are actually caused by forces arising from charges rather than from temperature gradients.
Yes. All I claim to measure is the temperature gradient. What's driving it, other than the fact that you have to have a density gradient as a result of the difference in temperature. That is required. You have to have maximum density somewhere in that column for this to occur. Now, the actual force that's driving it, I really don't know. I show it as cool water moving up, because I already know I have convection current. And if I add something, I can stop it. And depending on how much I add, is the way I stop it. Like I mentioned the experiment that's running now. I add 1/2 liter to 10 milliliters, and it has stopped it for over a week. So you're possibly right. I can't dispute that. And like my basic thing is I'm presenting data without major conclusions, suggestions and possible conclusions.
One more question.
Yeah.
Right. So why latent heat instead instead of releasing gradually, release suddenly? Shouldn't the latent heat release gradually? Because you show that latent suddenly.
Oh, it does. It releases within a millisecond, less than a millisecond.
Shouldn't it release in a more gradual?
No, only if your measuring device is out here somewhere. I have experiments where I have a column here, and I got a thermocouple here, and I put the electrodes in, and the electrodes will show latent heat. Latent heat is released 3 seconds before the thermocouple pick it up. So the latent heat is released where freezing first initiated, no matter where it is in the signal, that electrical signal travels through the water. And it's probably a lot less than a millisecond, but my resolution is a millisecond. And of course, if you put it out here, thermal out here, you see this, what you see in the classic textbook. But in reality, it's relatively instantaneous.
Hi, thank you for a very interesting talk. So, can you elaborate a little bit more about what you just mentioned with the thermocouple measurement? Are you saying that you're able to see the potential jump before the thermocouple shows temperature jump?
Oh yes. Like I said, I've been able to see it up to 3 seconds before. You see, when the latent heat is released, bonds are broken because you have to rearrange molecules. So an electric signal, an EMF is produced at that instant. And of course, you know how fast the electricity travels. So it is immediately seen immediately. So if the latent heat is released down, here, and your thermocouple's up here, that pulse has to travel this distance. But the electrical signal has been there and long gone. So another way to determine when latent heat is released, you don't need a thermocouple. Just have the electronic probe. Put a probe in there with a high beats meter, and you'll see it. Even when water is minus 0.2 of a degree, you see a very small signal. And